In this lecture, I'm going to give a very short intro about modeling continuous dynamics. Continuous dynamics are basically everything related to physical phenomena. A flow of liquid, the charge of a capacitor, gravity, all those kind of things. And continuous dynamics are ordinarily modeled through differential equations. You derive the physics equations and you can try to solve that in the time domain. There are techniques and models or mathematical tools such as Laplace transform that helps you do that in the frequency domain. That will be much simpler to deal with. There has been a complete set of theory around that to guarantee stability of your system and so on and so forth. This lecture is not going to replace any good control theory class, but gives this general overview of what happens when you can model the physics of a system and use that through differential equation and eventually simplifies that for your application. Let me first go through a couple of basic reviews. When you want to model a physical quantity, you need to go through the modeling physical motion. And one can review the standard 6 degrees of freedom, position, x, y, z, as well as the angular orientation, pitch, yaw, and roll. That will be useful to describe the 3D position of any object. You need to consider the mathematical domain of those various values. In the context of position, it's usually the mapping from R to R, where R represents the times and maps into the actual position in the 3D space. So it's possible to collect an actual position as a vector, x, y, z, that will depend on the period of time. You will note that in this set of slides, we're using very formal mathematical representations. This is essentially because modeling and cyber-physical system modeling has been formalized in the past decade or so in order to enable mathematical proofs as well as more powerful tools to implement a complete system out of the specifications. From there, and obviously that's getting of interest to our class when we look at the motor control system or the position for robots, you will need to consider the various derivatives of this position vector to understand the velocity as well as the acceleration. That's very basic physics, but it's always worth a reminder. Then you'll start applying all the various physics law. In that particular case, Newton's second law that will describe the relationship between the acceleration and the mass and the force associated with that. So you can, derive back your position knowing the mass and the force that is applied. So if you think of a sensor that measures the actual force applied to a system, you'll be able to derive the position. This is less well understood for us electrical engineers, but orientation applies similarly. So you'll have your values, the roll, the yaw, and the pitch. You can derive the position as well as the angular velocity and angular acceleration. That obviously makes a lot of sense when you consider a motor, which is the purpose of this, or the application, direct application of this lecture. One important notion to remember as well is the torque. The torque is the angular version of a force that applies when an object of a given mass is rotating around a fixed axis. The torque and the angular position of a given object are linked through the rotational version of Newton's second law that says that the torque is the derivative of the moment of inertia times the angular acceleration. Now, where am I going with all those notions that are seen either as very simple or as covered very briefly? Well, it applies directly to our DC motor control system. And when you try to model the actual system, you will have to consider all those different notions. Let's apply that to our DC motor. If you take a DC motor, when you apply a current through the motor, you will generate a torque. And this torque follows the equation torque is equal to the constant K times the current. So now, I would invite you to remember Newton's second law and its rotational version that say that the torque is also equal to the moment of inertia times the angular acceleration. So that will be j theta dot dot. In addition to that, when the shaft of your motor is going to spin, the motor is going to generate an electromotive force. It's the generator, the principle of any generators. And this electromotive force E is equal to another constant K times the angular velocity. Another thing that you will be able to do from this very basic system is to consider Kirchhoff's law. With Kirchhoff's law, you will know that the voltage V that you apply across your DC motor will be equal to the sum of the various voltage drops inside of the motor. So you will have the RI losses, so the joule losses, plus the electromotive force. And from the electromotive force, you'll be able to bring back the initial equation. That will be K theta dot. And you know the relationship of the current as a function of theta dot dot. So you'll be able to rewrite this complete equation using only theta, the angle. And from there, we end up having a differential equation of the second order. So to solve this equation, let's actually move that into the Laplace domain using Laplace transforms. The beauty of Laplace transforms is that the derivative over time becomes s times the integrated value, if you prefer, in the Laplace domain. So you'll be able to simplify this second order equation to a very simple equation that you'll be able to rewrite as a transfer function linking theta, the angular velocity, and the voltage applied across your motor. And what you'll get is a first order transfer function that will show a response of the first order typical to like an RC system. So now that we know that our motor behaves as a first order transfer function, we will be able to understand how it will behave and how we can control it further. So from there, I can create an actor model of my system which links my input, V, and my output, theta dot, with my transfer function inside. And that model will fully, relate what's going on in my system. So now if you look at the plot at the bottom right, where you have the relationship of the speed, the angular velocity as a function of the voltage that is applied, you will follow this exponential charge, which is what behaves when you apply the voltage the first time. But hey, what happens if you have a sudden change in the load? You will actually reduce the angular velocity. So what we want to do is we want to dynamically correct this error. How can we do that? This is what we'll practice in our lab, but we can use a proportional controller. The idea of a proportional controller is to actually compute the error between the speed, the velocity that you want, and the actual velocity you measure through what? Well, through our actual quadrature encoder that will measure the angular velocity for us. We'll compute this error, and we will use this error to increase the voltage if needs be, or decrease it if we go too quick, too fast. This complete loop will be able to show you what the actual angular velocity, and will be able to simulate the complete behavior of your system. While the proportional controller does a magnificent job, one can ask if this is enough. And actually, I will invite you to go through control theory and look at proportional integral controllers, PIDs, and so on and so forth to get a better response. We will also practice that in our lab. Now, so far, I only talked about continuous dynamics, right? So we're talking about the time domain, any varying quantity over time, but most of our systems are digital and use discretized models, for which you will have to actually consider not anymore Laplace transform, but Z transforms. And the beauty of that is that most of the end wavy theory I did talk about already will still apply in this particular case. Why? Because you can simply try to understand what is the notion between a discrete differential operation compared to the actual derivation of a function. And you will see, if you look at the definition, it's the limit tending to 0 of 2 time step 1 close to the other divided by this time. When you discretize your system, the time step won't be equal to 0, but will be a finite quantity. But still, the theory will be able to generally apply. Now, obviously, understanding models can be very challenging. Here's an example of what happens when you have 2 controllers, so you're controlling 2 systems, sharing a single CPU using your real-time operating system. Well, if you're using preemptive multitasking, which means that you will have preemption and you will have priorities associated with your different processes, it turns out that there is no way you can make this system fully stable. If you look at the 2 plots on the right, you will see that actually plant number 2 is stabilizing, while plant number 1 is diverging. One can immediately understand that it's creating a massive problem if you consider an industrial control of a plant or manufacturing. You don't want your tank to explode because your system was not controlling the level correctly. However, if you are using a non-preemptive multitasking, both systems will be made stable. And now, obviously, you will need to understand that before the design, and that's why why models are so important in cyber-physical systems. You will want to debug all those important aspects before you start doing the actual implementation.